redo this example again because last time when I come back to my office and I found yeah, we missed one information. So the last time I went through it is a little bit more rigorous, and so let's redo this one quickly today. The first half of the whole thing is the same. So basically for these questions, we are given this ratio. Basically from there, we will be able to determine the damping ratio. From this information here, we know this one is 2 pi zeta and 1 minus zeta squared, and that is a logarithmic increment or decrement. This one, by definition, we know is the log of the ratio between the x1 and x2. So x1, x2, from last time we know is if we have vibrations, this is x1, and this is x2. So representing is the ratio of the amplitude one period apart. That's the meaning of this one. Right now we are given is the ratio between the amplitude, the half period apart. So basically here we can do a little bit this thing. 1 divided by 1.5 at half period away from this one, and multiply 1.5 cubed. So again, this is the ratio of the amplitude half period away from each others. Okay. So from this ratio, basically here we know that x1 over 1.5 is 4. That is the ratio. Basically, that telling this is the amplitude x1.5. Here for amplitude, we only take the absolute value, and the absolute value we don't take any negative. And the same thing, this is 1.5 with respect to, again, the ratio half period away. So again, that is the 4. Okay. So from here, last time we come up with this, we can solving for damping ratio equal to 0.4037. So continuously, we should be able to solve for the damping constant and also the spring constant and the coefficient. So this one, let me copy the result here directly. Okay, so how can we do this one? Basically, we're using this the information C over M equal to 2 zeta omega n, and K over M equal to omega n squared. We're simply using the two equations, we obtain this. Okay. Now we come to this question here. We want to determine the amplitude. So basically here for this question we want to determine what is this one. The minimum initial velocity that leading to the maximum displacement. Okay, so basically we want to determine is what is the initial velocity here. So such that the maximum displacement is the less than 0.25 meters. Okay. So from this way, we're going to solve, really is to solve for the response. And from the graph here, that is the missing information. Thank you for kind of reminding me for that. From this graph, we do start from here. So that means we have a zero initial position, initial zero displacement. So from here, we can assume, because again, this is in sine curve, okay, because of the zero initial conditions. So we know that is in sine oscillations by reading this curve, okay? And we know this is the damped vibrations, and if we remember our total response, again, this is our generic pattern. So from the side, again, this is a very important concept. This is time. And for a vibration systems, x double dot plus 2 zeta omega n x dot plus omega n square x equal to 0. And here we have a characteristic root, and that is the root equal to minus zeta omega n plus j omega n 1 minus zeta squared. Okay. So from here we know the response, and based upon this information we can write is this basically this envelope is determined by the real part here. Okay, so E minus zeta omega n t. And the amplitude, the vibrations basically vibrating in this way. Okay, so for example here, let me say this is the maximum amplitude is equal to whatever the capital. And here the period of the oscillation, for example from peak to peak, that is a period equal to 2 pi divided by the oscillation frequency. Oscillation frequency is given by the imaginary part. So this is omega d. The value of the imaginary part is the oscillation frequency here. Okay, so keep those things in mind here. So right now for this one, we know this is in oscillation, so the frequency must be omega d. Okay? And omega dt. So that is the oscillation. And that gives us the form. And the amplitude of such oscillation is decreasing. So again, this is an envelope. So envelope basically is follow our patterns. So that is E minus zeta omega n t. And together with the certain constant capital X. So that totally uniquely defines the oscillation of the system here. Good? Okay, so keep those things in mind. So that is x over t. So starting from here, we can calculate x over t. So from here, we may be able to prepare for omega n. So from this information, we can either further prepare. So in this way, omega n for this one, the bent period equal to 2. I don't know why my pen is dying today. So let me change color. So then period equal to 2. Okay, so basically the 2 equal to 2 pi divided by omega d. That tells, I think also I did a mistake here. So 2s is the period here. So that's saying the line duration from here to here is 2s. So from there, 2s equal to 2 pi divided by omega d. So from here, we can determine omega d from this equation is equal to 2 pi divided by 2. So that is 3.1416 and radian per second. So therefore, omega n equal to omega d and by omega d equal to omega n times this one. And we already have the damping ratio calculated, so we can determine omega n. So omega n will be equal to 3.3388. Okay. So we have almost everything ready here, so we can begin to focus on these calculations. So the maximum, we're asking the maximum is to be less than 2.25. So here we have already is x of t. Capital X e minus theta omega nt and times sine. And how about we can plug in the numbers here? Or no, I think I better follow up my. Okay, we can definitely plug in the number here if you like. Let me follow with my notes. Okay, not to cause another mistake. So this one is e minus theta omega nt, and let me plug in omega d. Omega d equal to omega n 1 minus theta squared. Okay, so we have this one. So now to determine the maximum displacement, basically that is occurs at dxt dt equal to 0. Okay, so occurred at t1 or multiple values such that the reason why is this, again, if we have any functions, the maximum value of that functions occurred from graphically, we can see the maximum value occurred at this point. So this is our maximum value. So for example, this is x, this is f of x. The maximum value of this one is f maximum. That occurred at the certain value start corresponding to the slope of functions theta equal to 0. Simply taking this simple calculus. Okay. So from here we take out this one. So under this case we need to determine the x dot. Okay. So from here we do a little bit derivation from this formula here, and we see what happens. So from here we simply take the derivative, and derivative, let me focus on these terms first and then shift on to this term. So that will be minus theta omega n. I take the derivative on this term, okay, and then capital X e minus theta omega nt and sine omega n 1 minus theta squared. And then I take the partial derivative on the sine, and that will be equal to capital X. And taking the derivative on sine, basically we take the chain rule layer by layer getting to that one. A lot of writing, I know, but okay. So right now we stick with our requirement. We're asking the derivative equal to 0 in the way to determine the t. The value of t is such that the whole term is equal to 0. Okay, so basically we set up this equation equal to 0. Our goal is to solve for t. You good? Okay. So from here we can cancel some terms here. So so basically what I want to do is to move, I want to move this term, okay, I want to move this term to the left hand side of the equal sign. Okay. So again, I want to move the first term to the left hand side of the equal sign, and right now I take advantage of the whiteboard. So if I move this term to the right hand side, to the left hand side of the equal sign, then basically this term becomes like this. Right? Okay. So now we can cancel the common terms from the both hand sides. So here the x is a common terms. Okay, we can drop them off, and these terms is a common term, so we can drop them off, and omega n you can drop it off. Okay. So basically, the whole thing becomes. So here becomes zeta times that one. So let me do a little bit of rearrangement. So zeta, okay, sine omega n 1 minus zeta squared t, and equal to 1 minus zeta squared cosine omega n. Okay, so basically this is the zeta. Okay, and everything becomes like this. So we do a little bit another arrangement. So let me so basically I rearrange the terms in this equation become like this. I simply is move this one to the denominator of here and move cosine to the denominator of here, become like this. Okay, and this can actually give this tangent. Okay. So from here, because we already have the damping ratio being calculated, and so by doing this one, we know this is a number here. Okay, so you plug in, we can plug in 0.4037 and 1 minus 0.4037 squared. So basically here is a tangent. We can take our tangent, and within the argument of the tangent omega n and zeta has been known. So from here we can solve for the t will be equal to 0.3678 seconds. So that is the moment when the maximum displacement will occur. Okay. So under these situations, we simply plug in. And therefore, the xt, the maximum equal to the maximum when t equal to 0.3678. Okay, we simply plug in here. So that means capital X multiplied with e minus zeta omega nt times sine omega dt, and you plug in t equal to 0.3678. Okay, so from here, this one is less than 0.25 meters. Okay, so from there we should be able to calculate the maximum displacement, the amplitude. Equal to, I think, 1.42. Displacement. Initial velocity. So x, sorry, 0.455 meter. Okay, so therefore the x of t can be expressed by 0.455 times e and minus damping ratio. If you want to implement, you can implement with our numbers being calculated. Okay. So this is our response. And if you want to calculate the initial velocity, so that is the initial velocity, you simply take the derivative, or you simply take, I erase it. You simply from here, you take a derivative one more time and getting t equal to 0, then you will get the initial velocity. So basically here with this information, x0 dot will be equal to 1.4294 meter per second. That is our final answer. Yes.
Where did you figure out the capital X?
Capital X is this, because here we're requiring the maximum displacement equal to these numbers.
Yeah.
Okay. So we know our response, x of t equal to this. And we take the, we know from this calculation the maximum displacement occurred at this moment. So we plug in the t into these equations, into our response. We plug in t equal to this response, and the whole response is less than 0.25. So from here, we will be able to solve for x is less than this number. Okay? And any other questions?